For the third seminar, there's some handouts at the back which give the transparencies I'm going to be using today, plus a refresher on the reference and reading material. I'm going to do some recapitulation of some stuff we finished off on the other day, and then I want to talk today about the boundary conditions, in particular for piezoelectric materials, so that the electrical conditions will be discussed. I'm going to look at the types of propagating modes once more, take a second look at that, and see how that's affected by crystal symmetry. Those will be two linked items, and I do want to spend a bit of time today on layered structures, and the notes. Some of the notes on the layered structures are the last 2 or 3 pages of the handouts that were given out the previous lecture. So let's then recapitulate on some of the key ideas that we addressed last time. You recall that there was a critical matrix describing the material, which was given the symbol A, and we were concerned with the eigenvalues and eigenvectors of j omega A, which in fact describe the linear algebraic properties of the material. For piezoelectric, we have 8 eigenvectors and eigenvalues, and P and lambda are used to symbolize those. Now, what's important is that the vector, the 8-component vector that we are dealing with to describe the entire behavior, electromechanical behavior, has 8 components for the piezoelectric. And just to refresh your minds, I've listed them again in their order. The superscript T just means that it's in transpose. Normally this is a column vector. What we saw, which is important, is that at any depth, with respect to the free surface or interfaces, the vector tau can always be written as a linear combination of the modes. Now, each mode is characterized by an eigenvector and eigenvalue. So if you look back on equation 5, which I've repeated here, we just have the fact that at any location x sub 3, or z if you're using z as your coordinate system, that vector can be written as a linear combination of the modes of the system. This is a finite dimensional system, it's 8-dimensional, and so this is just the algebraic properties. This is important because this is what we're going to have to do when we try to fit to some boundary conditions. So I'm recapping that. At x3 equal to 0, if we give our origin as either the interface or the free surface, then of course e to the something 0 is unity, and we just have that the vector tau at the origin is just a linear combination of the eigenvectors of the system matrix j omega A. So that's, go back to equation 6a from the previous notes. And of course, as we did discuss to some extent last time, perhaps a little bit rushing just a little bit, for a half space, since the eigenvalues come 4 with a plus sign, plus real sign, the real part has a positive sign and the other half has a negative sign, in order to construct a solution for a surface wave problem in which the fields must vanish as we go down to negative infinity, we can only construct a solution to match the free surface by only taking the eigenvectors corresponding to the positive real part of the 8. So we have 8 eigenvalues. We can only use the 4 that decay with depth. And since the depth is the minus z or minus x3 direction, we can only take those that have the positive coefficients. So that block of the full eigenvector matrix pertaining to the positive real part roots, I refer to as P sub P, and of course that's an 8 by 4. And these, the Y sub P is of course a weighting vector, and since the Y here is an 8 by 1, we only take those 4 which pertain to the decaying modes, giving us equation 6P. Now I rushed a little bit through that the other day, and I think it's important to recapitulate that because that's very critical to how we construct solutions and look at different types of problems. So having said that, let's take a look at what we did say with respect to the surface acoustic wave problem. Here we have if the surface is free, we don't need that. If the surface is free, then we can write that tau at 0. And let me just look for the moment at the non-piezoelectric. Let me not mix it up with the electric terms. Here we have the 3 stresses are 0. The 3 particle displacements could be anything. And I've broken up this 8 by 4 matrix, P sub P, into an upper block and a lower block, because I want to isolate the first 3 equations. And this is equation 7 from the previous notes. And let me remind you once more that this P sub P matrix is going to be dependent on the particular value of phase velocity that you've put into your calculation. In a guided wave problem, we don't know the phase velocity until we've really solved the problem. And I'll come back to say a little more about that later. If we now take a look at the first 3 of these equations, then we have a 0 vector, a three-dimensional 0 vector, is equal to the upper 3 by 3 block of the P sub P matrix, which is a 3 by 3 matrix, times a set of weighting coefficients. And that basically is the statement of the boundary condition for that problem. And this is a standard AX equal to 0 algebraic type of problem, and we can only have a non-trivial solution for X, or the variables, if the determinant of that coefficient matrix vanishes. So this becomes the condition which must be satisfied if the value of phase velocity that we have used indeed is precisely the surface wave velocity. So that's the computational strategy, and this is the algebra underlying this computational strategy. Now, this is in a sense what I call a recapitulation of what we were talking about last week, and I think I'm going to pause here to just make sure that nobody has any additional questions they'd like to raise at this point on this basic issue. Now, what I want to look at today is look at some layered situations. So this is in one of the references that that was handed out, one of the papers, and the top picture that's sort of in view now is just a multi-layer stack. There's a free surface at the uppermost location and another free surface at the bottommost location. So this would be the situation that would arise if you had a laminated structure and you're propagating in a direction parallel to the laminations. That would be one situation where you do have propagation which is parallel to the interfacial planes. Another situation you might have is in a bulk wave compound resonator made up of a bunch of materials all in mechanical contact with each other, and now what you're concerned with is the transverse excitational properties of that. So these two classes of problems lend themselves to being analyzed using this matrix method that I'm talking about. Another type of problem is shown in the lower figure, in which we have a whole bunch of layers and then a substrate, and we have the top electroded, the bottom electroded, and we drive this with a sinusoidal signal. What we have now is a multi-layer bulk wave transducer. That's another geometry that lends itself to the methods that I described. I'll refer you to that in this particular reference, and you can see how it uses this matrix method to develop the situation. What is simple about this configuration is that we do not have propagation parallel to the interface, but in fact, all our propagation is perpendicular to the interfaces. This actually simplifies the problem significantly, and all you have to worry about is whether you're going to consider this as a current-driven problem or a voltage-driven problem. And in this case, if you choose it as a current-driven problem, you can work out the algebra for the solution of the amount of power that is launched into the substrate in a relatively straightforward manner. So that's the kind of problem that we can address. And of course, the surface wave problem with many layers is another situation which I will talk about. Let's talk about this in words for a moment and underline the power that I believe resides in the matrix method. This particular transparency is in the package you got last Monday. The first thing is that the matrix method, by virtue of the choice of variables, guarantees that all interfacial boundary conditions are satisfied. I'll show you exactly how this comes about in just a moment. From an analytical point of view, it's computationally the same as cascading multi-port networks using an ABCD type of matrix description. The other advantage is that no matter how many layers you have, because all rigid interfaces are automatically satisfied, the boundary conditions there, then you never increase the dimensionality of your problem. It always remains 8-dimensional, and that's another advantage. Now, when we have layers, the first headache you come up with is that you have a multimodal situation. There are many solutions to a structure which has layers, and all the modes that you find are dispersive. Let me remind you, dispersive means the phase velocity is a function of the frequency. The calculation of the dispersion curve is long, and sometimes it is not easy to distinguish which mode you are actually solving for until you look at the numbers that you're getting very, very closely. So everything isn't easy, but some things are easier than others. It's possible, of course, with multi-layers to synthesize structures which have desirable properties. For example, it's well known that by mixing certain materials, you can achieve some degree of reduction in temperature sensitivity of the surface wave propagation. You can tailor the shape of your dispersion by a suitable choice of materials and thicknesses. You can find combinations with layering which increase the electromechanical coupling coefficient of the system, and this is desirable in some cases because that is has a direct impact on device bandwidth when you get down to fabricating a device. Another possible advantage is you can have higher velocities with some situations by having layers. The technology, of course, is very challenging. As many of you know, it is not easy to grow good quality layers, particularly of piezoelectric materials, and achieve structures in which you have low loss and good mechanical performance. Some of the examples that you probably are all familiar with as far as layered structures are the ones like, for example, the zinc oxide and aluminum nitride on silicon. Those are structures that have been explored, and all of you have been hearing quite a lot about the zinc oxide diamond silicon combination, where silicon is the substrate, a diamond is the material which hopefully will give you a higher velocity, and the zinc oxide is the piezoelectric that allows you to get a handle onto this particular wave. So that's a few words about layered structures. There are many aspects that are of interest, and let's just take a look at some of these ideas. I did mention that with layered problems we can handle plate modes, we can handle bulk wave transducers, and we can handle surface wave multi-layered structures. The key relationship which helps you in formulating such problems is the fact that the value of this vector of variables at some location, let's say x3 plus h, is equal to the matrix exponential e to the j omega ah times its value at x3. So this exponential matrix is a transmission matrix which maps those field variables from their location at x sub 3, some arbitrary point, to a position h away from x sub 3, namely x sub 3, x3 plus h. This is an 8 by 8 matrix for the piezoelectric case, or 6 by 6 for the non-piezoelectric case, if you can read that on the transparencies. Now, let's take a look at the layered structure. Here we have, just remind ourselves about the exponential relationship between those vectors at different locations, and let's suppose we have an infinite substrate and then n layers. Well, from what we have seen earlier, we know that the vector, let's say that the x3 equal to 0 is the lowermost interface. So I'm writing tau at 0 is p sub p, yp0 as before. In other words, we have our linear combination of the eigenvectors corresponding only to those eigenvectors which decay with depth. That's why the subscript p is there. So this would be 6 by 3 and 3 by 1 for a non-piezoelectric. If we were dealing with a piezoelectric, it would be 8 by 4 and 4 by 1, because we have the extra variables that we have to keep track of. Well, if this is tau 0, and I know what this material is, let's say it's material number 1, then the value of the vector at the upper surface differs from the one at the lower surface through this exponential matrix, which I will put a box around. So the vector at this lower interface multiplied by this transmission matrix, where A1 is the A matrix for material number 1, and H1 is the thickness of material number 1, that will map the value from here to there. And now I think you can guess what's going to happen. I'm now going to say that at number 2, at the top of number 2 layer, I'm going to have the tau at the top of number 1 multiplied by e to the j omega A2 H2, where A2 is the A matrix for material number 2, and H2 will be the thickness of material number 2. Well, since I have a pairwise relationship, I will be able to eliminate everything, every interfacial statement, by just algebraic elimination, and I will get, if I call phi 1 this transmission matrix, let's circle it again. This is just a notation so that I don't have to keep writing this exponential. So the transmission matrix for material 1 is phi 1, and so this tau 1 is going to be phi 1 pp yp0, and then if I multiply by phi 2, I move up to the next interface, by phi 3, next interface, and eventually I get to the uppermost surface, let's call it tau sub u. It is going to be expressible as the chain multiplication of these transmission matrices for each of the materials times this substrate term, which we've discussed already for the free surface wave problem. And of course, since this is just a chain multiplication, I can just grind it out numerically. It's just matrix multiplies. What is going to be our boundary condition determinant now? Well, for the mechanical problem, no piezoelectricity, I have to have those 3 stresses vanish at that top surface. So that top surface means that I only need to worry about the upper part, the upper block of that transmission matrix. And if I write as big phi the equivalent transmission matrix for all the stack, I then get as my boundary condition that the determinant of this product, the upper half of this big matrix times p sub p, must vanish. Now, you realize that since each of these matrices are, in this case, 6 by 6, then the overall product remains 6 by 6. And when I get down to this statement of the boundary condition, since I'm only using the upper half, I only have the 3 by 3 determinant to compute. Now, if I hadn't used this method, I would have had to apply for the mechanical problem 6 boundary conditions at each interface, the stresses and the velocities. So I'd have had 6 statements for each interface, and you can imagine now the size of the problem exploding if I have more than 2 layers. And if it's piezoelectric, it's of course even larger. So let's sort of summarize those statements that I've just made. and reflect on that for just a moment and see if any of you want to clear up some issues. The key advantage then is that the dimensionality remains the same. No matter how many layers I have, I still have a boundary condition statement, which is the determinant of the matrix must vanish. And for non-piezoelectrics, this is going to be a 3 by 3 statement. For piezoelectrics, 4 by 4. Yeah. The question is with respect to the direction of propagation. The direction of propagation in all these is the x1 direction, which is perpendicular to the stacking direction, but parallel to the interfaces. It's the same geometry that we discussed before. Each layer is made up of a, I guess, let me recap your question. You're asking about whether each layer are uniform and infinitely long. Yes. In these problems, there is no x2 variation, the assumption being that that's infinite in that direction. There's no x1 variation except for the propagation term. So it's infinite in the x1 and in the x2 direction. It's only layered or finite in the x3 direction. Each layer is assumed to be made up of a homogeneous material which has a stiffness matrix, a piezoelectric matrix, and a permittivity matrix from which the A matrix for it can be constructed. The question regarding how to handle fingers, you don't handle fingers with this way. This is a completely separate problem. This is strictly a propagation problem. There's no device aspect to what is being talked about here. Yes, Jackie?
I'm still not sure I see why the propagation is that direction. The transmission matrix is something that's characteristic of the discrete stuff. Like A to B.
Yes.
And then you're using the relationship to relate in the stack. Your vectors to describe the field of the discrete stuff. So that is all these interfaces. I don't see anything to restrict the propagation.
Okay, let me, your question with respect to the fact that the A matrix is a material property is, and therefore why is the direction of propagation relevant, somewhere buried in probably the last talk, the stiffness constants and piezoelectric constants and permittivity constants all have to be referred to or rotated with respect to this coordinate system. So that the A matrix, although it's only a function of the material constants, has got information there with respect to how the material is oriented with respect to its crystalline axes. Before you do any specification for a material using this method, you have to take the material constants with respect to the crystalline axes and do the transformations required to express them within the framework of how the actual crystal is oriented with respect to your structure geometry. Yeah, so that's where that comes in, and that's a very good point because it tends to get pushed under the rug sometimes. Thank you for bringing it up. So that then summarizes how you do things, and using this method, and What I'd like to now spend a little bit of time on is back off and take a look at these boundary conditions and have a look at what happens if we have piezoelectric materials there. So basically we want to move over to the equivalent statement which we had earlier, in which we did not have an electric displacement term or a potential. Now, if we take the full piezoelectric problem, we have the electric displacement as a member of that vector, and the electric potential is another variable in the system. And last time, if you look back, we had expressed, this is something we already had earlier, but I just want to reformulate it now. These are our free stress on a free surface. So I'm back to a free surface, no layers, but piezoelectric. So we have the electric displacement as a new variable in the system, and we can write it, if we break things up into the two sets of equations as I did last Monday, and eliminate the weighting coefficient vector y sub p, then we can express the stresses and the electric displacement as a linear combination of the particle velocities and the electric potential through this matrix product here. This PPU is exactly the same or equivalent to what we used for the free surface wave problem, except that now this is 4 by 4. So PP is 8 by 4, its upper part is 4 by 4, its lower part is 4 by 4, and if you post-multiply PP's upper part by the inverse of the lower part, which is what this is saying, you can express these four vectors in terms of these. Now, just for convenience, I've called this a Z. It's in the nature of an impedance because it relates primarily stresses to velocities, but that's not important. So I can either write it this way, or as an inverse statement, and here something went wrong with somebody's printer, expressing the velocity field and potential in terms of the stress and the normal displacement. So this Y, big Y, is just the inverse of Z, and so if you want, it's just the inverse of this 4 by 4 matrix. Now, this only contains the mechanical boundary conditions. Okay, those three zeros represent the zeros from the zero stress conditions. We now have to worry about the fact that a piezoelectric has a potential wave accompanying it, and depending on what you do with the free surface, the fields will penetrate out into space. And so we have to handle this, and the next few words simply underscore the fact that each of these matrices are functions of the phase velocity, just as we had for the non-piezoelectric case. And if we fix the boundary condition properly, we will have found the right value of phase velocity. Now, if you just look at what's labeled as equation 10, you'll see the left-hand side is equal to some matrix times the vector, which has 3 zero components. And so if I just write the last equation, the fourth equation, is going to be j omega phi on the surface is equal to just one of the elements of this matrix times d3 because these three vectors, these three components are 0. If you just expand this out, of course, you have a 0 times the first column and so on and so forth. The only thing you have left is what I have as the equation where the arrow is pointing, which says that the potential is equal to the 4 element of that Y matrix times D3 0. Now, that is a constraint which is directly from the electromechanics. We haven't said anything about a boundary condition yet, except for the mechanical boundary condition. In other words, this statement, where there's an arrow pointing to it, is only true if you have a mechanically free surface, because it assumes that these three elements are 0. However, suppose you've set this, then of course you can always express the velocity as this times the elements of the 4th row. Again, it's just expanding and writing out the matrix term by term. And I've written this as equation 11, but really this is the one I want to focus on, and I want to point out that this is, in fact, the correct relationship between electric displacement and potential for that material. This is nothing to do with the free surface or anything else. Now let me ask you a question. Suppose I short-circuited the surface. What would happen to that equation? What should I set the left-hand side to? 0. So we have 0 is equal to something times d3. How can we have a non-trivial solution? Only if y44 is 0. So the short-circuit boundary condition is found when you identify the phase velocity which will make this 4 component of that Y matrix vanish. And of course, if you short the surface, it doesn't matter what you have above the short. There is no field propagating in the free space. So that's an easy one. You can see it, and it's relatively straightforward to work out. Yes? If those stresses are not 0, then in fact the potential is going to be a linear combination, and there will be 4 terms to it. Okay? So, however, remember, if those stresses are not 0, we're dealing with an interfacial problem. And what I mentioned earlier about multiplying matrices will then guarantee that you're satisfying interfacial conditions, and it's only when you get to the uppermost surface that you have to take a look at, okay, what do I do now? 0 stress, this must follow. So we've talked about the shorted BC, the boundary condition, and you can see it's relatively transparent from the way this statement comes out. But in general, we are not only interested in the short-circuited boundary condition, but also in the situation where we have an open-circuited. Here things get a little bit more complicated, but not much. If you write Laplace's equation in free space, and you look at the solution to Laplace's equation, you find that this equation 12 has to be satisfied. I don't have time to go through that. It's not a difficult exercise, and I suggest that you have a go at working it out. We can write it this way, or since I want to use j omega phi as a variable, I've chosen to write it this way as given in equation 12. So now, when we do not have a short circuit, we have to take equation 11 and combine it with this statement in order to find out what's the right boundary condition. And if you eliminate, for example, D3 from 12 and the preceding equation 11, then you get this statement which I'm pointing to now. And again, we have the situation that something times the potential is equal to something else times the potential. Okay, and since with the open circuited situation, a non-trivial solution means the potential cannot be zero, then the coefficient of the potential has to vanish in this statement, and that gives us equation 13. I've written it as a function. It's what is important to see is that this 4x4 element of this Y matrix that we talked about on the previous page comes in again, but it comes in with an added term. And how you handle this? Oh, we just worried about that. So what you have to do in order to find what I'll call the open circuited boundary condition, you have to find the phase velocity, which is going to make y44, when you put it into this equation, vanish. The short-circuited condition just requires that you find the velocity that makes y44 vanish. So they are different. Okay? And that's where you get a difference between the open circuit and the short-circuited velocity. And this is where the device designers and the people who analyze transducers need to know what is this, because it's a measure of how IDTs or transducers will couple to the fields. So I don't think I want to say too much more about this, unless there are some questions here. Okay. Let me talk a little bit. Then I'm going to, there is another sheet which I'm not going to discuss during this particular hour. It's entitled The Effective Permittivity, and I'd like you to take a look at it and see that, because it's just another way of formulating a boundary condition. And some of you who are working with piezoelectric propagating surface waves may have come across the concept before, and it's something that's been used by a number of authors. So let's now go into what I'm going to call a word mode, and stop showing equations for a little while. Let's talk a little bit about the mode types. And as in answer to a question, reiterate the geometry of the problem. We assume that any surfaces, whether they're free surfaces or interfaces, are perpendicular to the x3 or z axis and parallel to the x1 axis. I will always take the x1 or x-axis as I sometimes use x1 and I sometimes use x3 here. So these are equivalent statements. So that's back to the question Jackie raised a moment ago. We always, when I do this formulation, the first thing I do is take a list of all the materials being used, how they're oriented, and rotate all their constants so that everything is referred to the same coordinate system. Then I can construct the A matrices for each layer and proceed with whatever computational things I am trying to do. Now, the XZ or X1, X3 plane is the sagittal plane. I did mention that the first lecture. And when we talk about a Rayleigh surface acoustic wave, strictly speaking, we should be talking about a sagittally polarized wave. Now, this is not universally adopted, so it just happens to be my preference. So, wherever possible, I would say sagittally polarized rather than Rayleigh wave, just so that you're sure people understand what you're talking about. There's also waves which are polarized perpendicular to the sagittal plane, and these are called shear horizontal or SH waves, and the Bluestein type of waves are in fact of that type. Now, what are the different modes that we can have? That depends on a number of factors, and I'll go into that in just a moment. But we can have a generalized piezoelectric mode, which means every single field variable is coupled. The polarization is arbitrary. It's in neither of those categories that I just listed. And that is the most general type of wave. By the way, this categorization or classification applies whether we're talking about surface wave or plate modes. The same breakdown applies, except we use different names for them. For example, the next type of wave which is of importance is where the particle displacements are polarized in the sagittal plane, but the electric fields are coupled to these particle displacement. This is a stiffened Rayleigh or a stiffened sagittal solution. The word stiffened is used to indicate that it's piezoelectrically coupled. It's nothing special about that. If you're dealing with plate modes, then that kind of a wave, which is polarized in the sagittal plane and is accompanied by electrical field variables, we would call a stiffened Lamb wave, if we're dealing with plates.
Say a little bit more about stiffened in terms of, is there some sense in which it's like effectively increasing the values or something?
No.
Why does it use the term stiffened?
I've used the term stiffened to indicate that piezoelectricity enters into the picture. You cannot have what we do with bulk waves of expressing stiffness constants as equivalent constants by eliminating the electric field variables from the equations, and the result, what you get left over, is a set of what we call stiffness constants, or stiffened...
Piezoelectricity have the effect of decreasing the velocity with respect to if the constants were, I mean, like if you have stiffer material, then the velocity goes up. It's curious why they stiffen instead of soften.
The phrase, as you say, when we use stiffened, we mean the velocity usually increases, and this is only true for bulk waves. You can only make that statement for bulk waves where you can show that, in fact, That's exactly what happens in all cases when you have piezoelectricity. You cannot say that in general for surface waves of any kind. So one has to do the number crunching to figure out what is really happening. So it sometimes also happens that you have in a material purely mechanical solutions, sagittal solutions which are purely mechanical, in which the actual piezoelectricity just does not enter into this. This can happen by accident of a combination of material constants, or it can be determined by crystal symmetry, and I'll say something about that in just a moment. SH piezoelectric then would be the Bluestein-Gulaev modes. For plate modes, you would say they're Stiffen-Love. Yes, you would say Stiffen-Love. And for purely mechanical, you would just call them Love solutions. So that's, in words, what happens to the solutions. Let me take a little look at how crystal symmetry has an effect on our solutions. First of all, very often there are sufficient conditions determined by crystal symmetry which allow you to know right from the beginning that you are going to have uncoupling, that you're going to have a pure Rayleigh wave, for example, a pure mechanical solution in the sagittal plane. This will typically give rise to situations which depend on direction of propagation, depend on crystal orientation, and the most important thing that results because of this symmetric impositions is that the order of the problem becomes lower than 8. Okay? Now, there are some examples on the remainder of this sheet which I'd like you to take a look at, but I'm not going to discuss them right now. Just take a look at those. What I do want to take a very quick look at is a classification scheme. This has not been, I don't think I've distributed that, but it was distributed as one of the pages of the Farnell and Adler section that was handed out right at the beginning. So you'll find this table there. And what happens, what I want you to look at here is the order of the characteristic polynomial. The generalized problem is 8th order, as we've looked at before. The purely mechanical problem is 6th order. The sagittal piezoelectrically coupled one is 6th order. The purely mechanical sagittal one is 4th order. The stiffened horizontal type of solution is 4th order, and so on down this line. Please take a look at table 3, which you should have as being handed out the first time around. So that's basically what we have. In that same reference, which was also distributed in the beginning, there is a table 4 which gives some examples with respect to the particular crystalline type as to how this comes out. And I think what I'd like to finish off with today is the hint that we have non-leaky guided waves, and those are the most common ones, the ones everybody knows of. I will be talking about pseudo surface waves, and I'd like you to take a look at what has been handed out, and in particular to take a look at the two references which have a title. It's a 1994 article which I wrote, which has the title, which has pseudo surface waves in it. That'll explain some of the problems involved there and how they're handled. And also I will be discussing high velocity pseudo surface waves. And I think on that point, I think we'll cut off for today.